Hi there, this video is for section 9.1 and 9.2. We're going to be showing you how to model differential equations using direction fields. Perhaps I need to start with defining some words, what a differential equation is, and what a direction field is, because we're going to be modeling one using the other. So a differential equation is basically any equation that has a derivative in it. You can kind of think it as a derivative equation. The derivatives can be anywhere. They don't just have to be on the left-hand side like dy dx equals, although we are going to start there and then get some more complicated examples in future videos. A direction field is basically a graph. We're going to be graphing this differential equation, this derivative equation. Remember that the derivative measures slope of the tangent line, right? The instantaneous rate of change at a particular point, which graphically is the slope of a tangent line. Okay, let's look at some examples on how we're going to do that. So the first thing I'm going to be doing when I get a chance to scroll here is letting you know that when you look up direction fields, sometimes they're called slope fields. There's not really a preference for one over the other. You'll see direction field as often as you see slope field, two different expressions meaning the exact same thing. So the first example here I have y prime of x is equal to y over 2. And just to be clear, this is the same thing as dy dx equals y over 2. So this is a differential equation because it's an equation with a derivative in it. And it can have other variables. In this case, it has the variable y. It doesn't have the variable x. And what our mission here is to graph this differential equation, however that's going to work, and to see what the graph shows us. So first of all, let me go through the steps of how to graph this differential equation. So in this grid I have here, we have the x variable and we have the y variable, and we're going to be graphing the derivative variable. The derivative variable is slope of tangent line at a specific point. So we have lots of points. There's a whole grid of points here, and I'm going to make a little table of data, x, y, and the slope. And we really have to fill this in with a lot of points. So for example, I could have an x of 0 and a y of 0. I could have x of 1 and a y of 0, or maybe 0 comma 1, and then 1 comma 1, and 3 comma 4. And I mean, there's a lot of points here. So yes, there's a lot of things to do here. But we're going to look for some patterns, because with patterns, we'll be able to do this much more efficiently. All right, so let's start with 0, 0. Now, you may notice if you look at this differential equation, this equation with a derivative in it, there's no variable x. Dx is the change in x, but x is a variable. Dx is not the same as x. So the only thing we have to do is divide y by 2. So in 0 comma 0, we'll do 0 divided by 2, and we'll have a slope of 0, which means at the point 0 comma 0, which is right here at the origin, I need to draw a slope of 0. A slope of 0 is a flat line. So I'm going to do right here a little flat line, sort of representing that little slope right there. At that particular point, the tangent line has to have a slope of 0. So you can imagine that as like the instantaneous rate of change at that particular location. All right, so let's look at 1 comma 0. 1 comma 0, once again, there's no place to put an x in. So even though x is 1, it doesn't really affect our differential equation because it just says y divided by 2. So once again, it's 0 divided by 2, which is 0. So at the point 1 comma 0, which is right over here, 1 comma 0, x is 1, this is the x-axis, this is the y-axis. At 1 comma 0, the slope is 0. I'll put another little line right there. My next point in my chart here is 0 comma 1. 1 divided by 2, the y divided by the 2 would be the slope. Well, that's just 1/2. So at the point 0 comma 1, I have a slope of 1/2. So that's certainly not a slope of 0. A slope of 1 is perfectly 45 degrees, right? Slope of rise of 1, run of 1, that was a slope of 1, that would be 45 degrees. We have a smaller slope, a half as big slope, So it should sort of, be half as big. In fact, it's rises 1, runs 2, right? It's a 1/2 slope. So at this point, 0, comma 1 means x is 0, y is 1. I'm going to have a slope which is not 1, but a half. So I'm going to have our time, making it precise, but, we'll do an approximation. That looks to be like not quite 1. Maybe I'll make it a little bit flatter, something like this. We're just trying to get the idea. That's about like not a 45-degree, but like, I guess half of that, 22.5 degrees. All right, so we can continue doing these. 1, comma 1, you take the y value, divide by 2, and you may have noticed that there are definitely some repeats, right? At 1, comma 1, we also have a slope of a half. So let's think about how we can do this more efficiently. All right, so we notice that only the y really matters in this particular, simple example of a differential equation. So as long as the y is the same number, like I have 0, 0, 1, 0, what about 2, 0? Let me go back to green. What about 2, 0? Again, the y value is 0, so we're going to have 0 divided by 2, so we're going to have another slope of 0. In fact, anytime we have a number, comma 0, even if we have negatives, -1, comma 0, it's always going to have a slope of 0, 0, 0, 0, right? Because the y value is being 0, being divided by 2, and we get 0, which means all along this axis at 2, comma 0, 3, comma 0, 4, comma 0, -1, comma 0, all these are going to be 0. Some of you might already starting to see another pattern. We have a couple of halves here. Those came from when the y value is 1. 0, comma 1 gave us a slope of 1/2. 1, comma 1 gives us a slope of 1/2. So you might be able to guess now, just make some more space for things, that if I had did 2, comma 1 or 3, comma 1 or -1, comma 1 or -2, comma 1, all those are going to have a slope of y divided by 2. The x isn't in play because the equation doesn't involve the x. We'll get to some x and y equations in a bit. I just want to start with an easy one. So all along, when y is 1, we're going to get a slope of a half, 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 half. Right, and I could just keep doing this as long as I can sort of draw a slope of a half. What about when y is 2? So when y is 2, you could have x is 0 or x is 1. But as long as y is 2, the slope is going to be, well, it's y divided by 2. So 2 divided by 2, well, that's just 1. So when y is 2, whether it's 0, 2 or 1, 2 or 5, 2 or any of those 2s, we're going to have a slope of 1, which as we know is a 45-degree angle. So we get 0, comma 2 is a 45-degree angle, 45-degree angle, 45-degree angle, like that. And continuing this way, you can graph slowly but surely the direction field. So we're basically making this giant graph of little slope lines, right? Which is, I guess, why some people call it a slope field, right? Because it's a bunch of slopes in the field. 3, if y is 3, that would be 3 divided by 2, which is a little bit steeper, like this, right? And so you can start seeing some patterns here. 3 over 2 is 1.5 bigger than 1. What about going to negatives? What if y is like a negative number? So let me get rid of some of these just to reuse some space. All right, there we go. So what if y is like -1? Again, it doesn't really matter what x is because the differential equation doesn't depend on x. And what is the slope? Well, it's y divided by 2, so it's -1/2, -1/2, etc. What does -1/2 slope look like? Well, +1 slope is increasing at exactly 45 degrees. -1 slope would be decreasing at exactly 45 degrees. -1/2 is half as steep. So it'd be kind of like halfway between a decreasing 45-degree line, sort of like, this slightly, it's basically rise or down 1 and over 2. So rise -1, run 2. So it's kind of like this flatter line like that. So let me draw a bunch of those in there. All right, so we have a decreasing slope of a half. Let me go back to my red. So kind of a flattish line like this. All right, and then you might imagine what happens when y is -2. When y is -2, we're going to have slope of negative 2 over 2, which is negative 1. That's that exactly downward 45-degree line. And you can probably start to see a bunch of new patterns here for these different things. So at negative 3, it'll be a slope of negative 3 halves, which is steeper, like slope of negative 1.5. I'm just approximating these. Maybe they're not so great approximations. You can do better than me, perhaps, but we're just getting an idea of what these look like. The study of differential equations and direction fields is very complicated. We have a whole course dedicated to differential equations and their solutions via direction fields and other ways. So if you're taking a lot of math, that will be, after a bunch of calculus classes, you'll be able to take a course in differential equations, which are quite useful in lots and lots of different fields. All right, so suppose we've done all of these little lines here. We've had enough patience to draw out, a sufficiently large direction field. That is what we're trying to get you to do in part A, right? Sort of do the direction field, show all the little slope lines, and that's the graph of the differential equations, the visual image of a derivative equation. It's kind of got three variables. If you think about it, it's got the x variable, the y variable, and then what we're graphing is a third thing. We're graphing the slope, which is essentially a different thing because it changes. The slope is 0, or the slope is a half, or slope is 1. So in some sense, this is sort of a two-dimensional image that's using to project a third idea, a third quantity called slope. In other words, a third variable. All right. So what do we do with this thing? Well, one thing we can do is we can talk about the solutions to this differential equation. A solution is basically an equation like f of x, or in this case y, that makes it true that dy dx is equal to y over 2. So you may be able to think of some equations where the derivative of that equation is exactly the same as the equation divided by 2. But even if you can't think of an actual equation, we can graph what the equation looks like. So I have this example, or this parts B and C here. We want to graph a particular solution. There's lots of solutions to these differential equations because of the whole plus C thing when you add C when you're anti-differentiating. But again, even if you can't anti-differentiate this, we can graph any solution. So the first example I have here is finding a solution that passes through the point 0, 1. Well, where's 0, 1? 0, 1 is right here. And we know that that is part of the curve, right? The curve goes through 0, 1, but we also know at 0, 1, the slope of the tangent line is already given by that little red line. That was the slope of 1/2 I was trying to draw there. So we know that whatever the graph looks like, whatever this shape is, at that point, 0, 1, the slope of the tangent line is 1/2, which means that's the direction of the graph at 0, 1. Remember, the tangent line, if you have a curve, the tangent line not only touches the graph at that one place, but it's like, in that same direction at that place, right? It goes closer and closer and closer, touches or kisses at that one little point, and that's sort of the direction of the curve. The instantaneous rate of change of the function is given by the slope of the tangent line. So we know that the graph is going in that direction. But if you go in that direction, you're going to hit one of these other slope, which is a little steeper. So we know that by the time it gets over here to like 1.5 comma 2, if I'm just going in that direction, it's going to go steeper. It's going to have a slope of 1, in fact. So maybe it goes up this far. And when it hits 2 comma 3, it's even steeper. It has a steeper graph. And we can go backwards. So instead of going to the right from 0, 1, we go to the left. So we know it's a half, right? So it's still going down by a half. And over here, it's going to hit somewhere where the slope is even smaller. So it's going to go even flatter and even flatter. And there is a slope of 0, so it could get closer and closer, but it can't really get to 0. So it's going to sort of get closer and closer and closer. So, and this is going to keep going up and up and up. If I drew more of the little lines, you would be able to follow the more of the lines of what it looks like. So that, my friends, is what the graph of the solution to this derivative equation, this differential equation, that also passes through the point 0, comma 1. And yes, this is an exponential curve, and the solution to this is an exponential equation. Remember, the derivative of e to the x is the same e to the x. This has a divided by 2, so it's a little bit more complicated than e to the x, but it's basically the same kind of function. Some exponential function where I differentiate it. I don't get it back exactly the same function, but I get something of that function divided by 2. All right, so let's try one more. We have this one where it says graph the particular solution that passes the point -1, comma -1. So if you want to pause the video and see if you can draw the solution through -1, comma 1, or on your paper, or if you just want to do it sort of visually, like with your finger on the screen, -1, comma -1, give it a go if you like. See if you can figure out what the solution looks like for that one. All right, so hopefully you had a chance to give that a try. At -1, comma -1, I have a slope of -0.5. I'm going to be following that. And then when I hit the next little line, I'm going to be following that. And I'm just going to sort of do the artist trick of just drawing little short segments. And then I'm going to let the slope lines guide me as to where to go next. All right, so if you got something like this, then you did a great job in visualizing what the solution looks like for -1, comma -1. This is also an exponential function, but it's going down. So it has like a negative exponent or something to do with making it go down instead of up. If you remember from your pre-calculus, it's kind of a reflection over the x-axis. So the y values have turned to negative y values, that kind of thing. All right, so that was my first example. My second example is very similar to this, but the idea here is we are graphing a differential equation using a direction field, and then based on the direction field, we can graph even solutions to this differential equation. We are going to solve some of these analytically, which means, by hand using equations, but many differential equations are extremely difficult to solve by hand, if not impossible, which again is why we have a course on dealing with differential equations. So we're going to be using the simple ones for our introduction to differential equations in this class, but they do get rather complicated very quickly. Just be aware they're, not as simple as I am making this first example seem. All right, I'll do one more thing, which is I'll bring technology into this. I'm going to go to Desmos, and I have, oops, maybe not over here. Maybe I'll go to this Desmos. Here we go. So I've set up here a little differential equation or a direction field grapher. The way Desmos works is you put gxy in here as the derivative. So I said let gxy be the derivative. And in our particular situation, our derivative is y divided by 2. And let's see if it makes it. There it goes. So this is the direction field that Desmos made for y over 2. You can see that when y is 1, we get little lines here about 1/2 slope. When y is 2, we get 45-degree 1 slopes, and they get steeper. And here's their negative versions. And here's the zeros right here. Right along the axis, we have zeros right there. And they have a little dot here. You can move the dot around. And you can see as I move the dot around, the slope changes. Right? So the little dot, you can put anywhere you want, and you can kind of see where it goes. If you want, you can start at, like, say, -1, comma -1. Whoops, so down here. And you can follow the little line and just keep following the line, and you'll get your exponential, or at least your solution. It is exponential curve. Anyway, so that's a little fun little tool. There's lots of different ways of using technology to help you graph these things. And I just wanted to make sure you knew about that there are definitely programs that can do all the calculations for you and draw on the little lines. It's kind of nice to do it, at least once or twice yourself, just to get the feel of how it works. But it can be quite tedious. So I want to make sure that you know that technology can help eliminate some of that tedium. All right, so let me go back to the tab here. All right, so let's look at another of these examples. So here's a direction field for this function. So here I have y prime of x equals x minus y. So here I have both variables x and y in my differential equation. And I can make a little table here. Again, I have an x value, a y value, and a slope value. And I'm going to put in a bunch of numbers here. The idea is to try to find some patterns. Maybe some of you are already thinking about patterns of what's going to work here. But let's do a couple together. If x is 0 and y is 0, so we're talking about the origin, the derivative equation, which is right here, is x minus y, which is 0 minus 0, which, yes, indeed, is 0. So I know at the point 0, comma 0, I have a slope of 0. So once again, like before, we have a horizontal line at 0, comma 0. What about 0, comma 1? 0, comma 1, it's just x minus y. So I'm just literally going to go x minus y or left to right. 0 minus 1 is negative 1. So at the point where x is 0 and y is 1, you have to find that place. So x is 0, y is 1 is right here. At that point, you have to draw a slope which is negative 1. So going down at 45 degrees. Right? 1, comma 0 would be 1 minus 0. So far, we don't really have any repeats. 1, comma 0, which is x is 1, y is 0. We have a slope of positive 1. So that's going upwards at 45 degrees. 1, comma 1 would be, well, that's just 1 minus 1, which is 0. We have our first repeat. So at 1, comma 1, x is 1, y is 1, we have a slope of 0. This is going to be 2 minus 1. I'll just do a bunch in a row. 2 minus 1, 1 minus 2, 2 minus 2, 2 minus 3. So this is a slope of 1, negative 1, 0. You starting to see some patterns here? Okay. If you do, that's good. If not, that's okay. But you can keep doing these until you start to see some patterns. All right. So I did 1, comma 1, 2, comma 1. 2, comma 1 is right over here. It has a slope of 1. 1, comma 2 is x is 1, y is 2. It has a slope of negative 1. 2, comma 2 is 2 minus 2 is 0. And 2, comma 3 is up here, has a slope of negative 1. All right, so if you haven't seen one of the patterns, there's several patterns here, but if you haven't seen one of the patterns yet, I can tell you that apparently there are the diagonal lines. Like on this diagonal right here, it's like 0, 0, 0. When it's 3 minus 3, it's 0. When it's 4 minus 4, it's 0. So you have, when x and y are always the same, you have a slope of 0. When the one is bigger than the other, right? You have either a slope of positive 1 or a slope of negative 1, right? So here we have y is 1 bigger than x and a slope of negative 1. Here we have y is 1 bigger than x, slope of negative 1. Here we have y is 1 bigger than x, slope of negative 1. So therefore, when we have like 0, comma 1 or 1, comma 2 or 2, comma 3 or 3, comma 4, we're going to get slopes of negative 1 each time. And we also get a slope of positive 1 along this diagonal right here when x is 1 bigger than y. And those actually, I shouldn't stop here. They actually go down here as well with the negatives or with the positives. Negative 1 minus negative 1 is 0. Negative 2 minus negative 2 is 0, etc. It's still the same calculation for each of these things. And these, I'm just going to draw in some 45-degree angles here going down for that one over there. And so each of these diagonals, we kind of have, the same kind of calculation. And then, we can graph more and more and more of those in there. Again, depends how much patience you have. We can also use our Desmos. The derivative equation is x minus y. So if I go up here and I change this, instead of y over 2 to x minus y, hopefully it'll do the equation for us. There we go. And so here's the diagonal where the slopes are always 1. Here's the diagonal where the slopes are always 0. Here's the diagonal where the slopes are always negative 1. These are the ones we're starting to graph. And you can kind of see, there's a whole myriad of these things where you can see, the slope at that particular point. Once we have this crazy thing, you notice that they're getting very, very vertical over here and over here. These are going down vertical, so they're very large negative numbers. So this is where, like, the x number and the y number make a very large negative when you subtract them. And here you have very large positives. So this is where the x minus the y make a very large positive number when you subtract them. And we can imagine taking any point. Suppose we start at 2, comma 2. There's at 2, comma 2, there's a horizontal line. So I follow that horizontal line and I hit here. So I go up. I guess I could have gone up a little earlier, but going up like this, and then it goes sort of flat again and up again. So here it's going to be sort of wiggling right around that 45-degree line, right? If you started right on the 45-degree line, suppose you started here at 1 comma 0, then the slope is going at a 45-degree angle, going up by 1, and the slope keeps going up by 1. So 1, 1, 1, 1, 1, 1, 1. If we started over here, let's suppose at some negative value, let's say, here we have like -5 comma -5 comma +2, and going down and down, and it starts curving a little bit, and then it curves, and then it follows this 45-degree line again. So, you can kind of sketch out, I'll put a solution depending on where you start from. In the lecture notes, I just made up some numbers just to give you an idea. So once we get our like fully formed direction field, which I didn't spend a lot of time making this, maybe I'll just pause the video and just put a bunch of more lines in there so that you can kind of see what it looks like. Okay. Okay. So I did a few more. It's tedious for me, so I didn't do so many. I just got tired of doing them. Anyway, so I just want to do them a little bit more so it's easier to see what the graph of the solutions are. So for example, in part E, it just says start with the point 1 comma 0. So that's x is 1, y is 0. That's this right here. That's a slope of 45 degrees. So I would go to 45 degrees till I hit the next line, which is also 45 degrees. So I go to the next line. So it's also 45 degrees. So if I start with the 0.1 comma 0, my solution looks like a very straight line, right? With a slope of 1 and a y-intercept of -1. That's like y equals 1x minus 1, right? That's the solution to the differential equation if I know that it goes to the point 1 comma 0. What if it goes to the point 0 comma 1? Well, I got to find 0 comma 1. 0 comma 1 was right here. It has a downward sloping line there. So I'm going to follow that. And then I get a sort of more flatter one, and then I get to the 45-degree one. So it kind of goes like that. And over here, it gets steeper. And I didn't draw them in, but if you remember from the Desmos version, it gets steeper and steeper and steeper. So this is your graph here. Definitely not a line. Maybe a hyperbola or something like that. I mean, we don't know how to solve this quite yet because we haven't learned that yet. We'll do a little bit more in 9.3 on solving differential equations, but right now we're just going to get a visual image of what's going on with these differential equations, with these graphs of their direction fields. All right, so that's a couple of examples of graphing a direction field and then understanding what the solutions to the differential equation visually look like. All right, so let's do a couple more problems of a little slightly different version, and then we'll be done with today's video. Okay, so for the last few problems here, what I have here, let's put some more space. Draw a line here just so you can visually see what's going on. We're on part G right now. I did the graphing of the solutions through the points 1 comma 0 and 0 comma 1. That's above. And now in example G, it says there's a differential equation. This is a much more complicated differential equation. It has a second derivative in it. It also has a first derivative in it. It also has y's and x's and cosines. This is a very, very complicated differential equation, right? Y prime equals 2y prime minus y plus x minus 2 cosine x. So we could definitely graph the direction field for that. We can use a technology program to help us do that. We could do it by hand, which is quite tedious. The second derivative is hard to graph. Usually we don't do graphs of second derivatives in the same way as graphs of first derivatives, because the second derivative is how the slopes change, right? It's the derivative of the slopes. It's the derivative of y prime. So it gets more complicated to graph. Again, not our course, much more complicated than we're ready to deal with, but I'm just trying to give you an introduction to this idea of differential equations and what their solutions look like. So what's the gist of these last couple of problems that I'm going to run you through for the video here? Well, we want to be able to know whether a proposed solution is indeed a solution. So we have this differential equation right here, this complicated differential equation, and we have a question. The question is y equals sine x a solution? So a solution would be an equation that makes that thing true, right? So, just like when you're doing basic algebra, you're checking to see if x equals 5 was the right answer. You plug in 5 and you see if you get the equal sign to equal out. And you're like, yeah, okay, it works or it doesn't work. We're doing the same thing here, but with much more complicated equations, specifically differential equations. So we're going to have to be able to plug in into the left side and the right side to see if it works out. All right, so we know y is sine x. We're going to have to find out y prime because we have to plug in y prime. If I differentiate sine, I get cosine. So I know y prime is cosine. And if I differentiate y prime, I get y double prime. And the derivative of cosine is negative sine. Nothing surprising there. Let's see if my pen will work a little bit. Yeah, it's a little slow right now. All right, there we go. All right, so I'm just going to plug stuff in, just like you're plugging in for other equations. We're going to plug stuff in here. So y double prime, we know what that is. That's sine x. So we get sine x equals. Now I'm going to put a question mark over this equals. We don't really know it's true. We're trying to determine whether this is true. So I'm going to put a little equal sign there. 2 times y prime. Y prime is cosine. So 2 times cosine. Oh, again, my pen's a little slow. Maybe too slow. Okay, I'll just try to get to work better. And then minus y. Now y is, well, it's right up here. Y is sine x, right? It was given as the original information, so that would be sine x. And then we get, well, that's minus y. Then we get plus x. So literally plus x. And then we have a minus 2 times cosine x. Yeah, it's going to look bad. All right, let's see if I can fix it up a little bit. All right, sorry about that. Minus 2 cosine x. All right, so now you just have to do the algebra and see if those two sides are equal to each other. So we got sine x on the left. On the right-hand side, what do we have? We have a 2 cosine x and a minus 2 cosine x. That looks nice. 2 cosine x minus 2 cosine x, that's 0. Then we have a minus x sine x and a plus x, and those can be combined together. That's just minus sine x plus x. So is that the same thing as sine x? Well, it certainly doesn't look the same. Now, looks can be deceiving. So mathematically, we would like some evidence that they're not the same. So how do you provide evidence other than visually saying, okay, well, they don't look the same, right? So certainly visually, we could say they don't look the same. There was a time in your life where you thought 1/2 and 0.5 were different values, right? Because it looked so different, right? 1/2 and 0.5, they don't look the same. But of course, we know they are the same. So looks, we don't want to completely go by there. But you can just throw in a number, right? So you can throw in an example of pi or something like that, right? So you just do a little example. Sine of pi. Now, if it works for pi, that gives you evidence that they are in fact the same. If it doesn't work for pi, then we know they're not the same. We don't need to actually do any more investigation. So this would be minus sine of pi and then plus pi. And if you remember a little bit of your trigonometry, you might remember that pi, which is like 180 degrees, like halfway around the circle, has a y value of 0. So it has a sine of 0. So we know this left-hand side, the sine of pi is 0. Negative 0 is same as 0, and then plus pi And I am fairly certain that 0 does not equal 0 plus pi, so not a solution. So y equals sine x, our original question, this equation here is not a solution. Is not a solution. All right. Painfully trying to write out using my stylus. All right, so the answer is no. And our evidence is right here. We found the different derivatives, plugged them all in, simplified. We got a result that we could show was not equal to each other. So we can put like a little no here. They're not equal to each other. And therefore, we know that's not a solution. All right, so the last problem I'm going to invite you to try if you want to pause the video and see if you can give the last one a go. It's a very similar question. It's the same differential equation, in fact. It's still this crazy second derivative equation. We call it second order equation, by the way, if you want to be fancy about it. So the second derivative equation, y prime equals y double prime equals 2y prime minus y plus x minus 2 cosine x. And we have a new proposal. So the question is this guy a solution? Is y equals sine x plus 2 a solution? So I invite you to pause the video and give it a go. See if you can answer yes or no and provide some evidence as to why. I'm going to pause the video and write out the solution because my pen is working very slowly. That way you don't have to wait through me writing very slowly. And so pause the video if you will, and then in a few moments, you will see the solution written out. Okay, so hope you gave that a try. I had to move the screen over a little bit because I was running out of space. So here we go, my solution. I found the first and second derivatives. There's these guys over here in red, and I just plugged it in. So this is plugging in over here. And then I combine like terms, a lot of things added to 0, and I ended up with negative sine x is equal to negative sine x. And that is exactly the same thing on both sides. So yes, in fact, this is a solution to the aforementioned, the above written differential equation. So when you're doing the homework, it'll ask you whether or not something is a solution. You just got to plug it in and do the math, and then you'll be able to know whether or not it is. All right, so hopefully this video is helpful. And if you have any questions, need help with anything, remember, I'm always available. Just reach out via email or drop by my Zoom hours, and we'll get you going. All right, hope you have an enjoyable day.